Okay, so we are still in module 4 and we're starting a new section on direction fields and numerical methods. So I'm gonna tell you guys right now, this is completely different than everything else that we've done, altogether different, okay? We're going to be drawing direction fields for a given first order differential equation, using a direction field to draw a solution curve of a first order differential equation, and using Euler's method to approximate the solution. So what is a first order differential equation? So a differential equation is, so let's just do a definition. So a differential equation and I'm going to say an ordinary differential equation is an equation containing an independent variable usually x or t, and a combination of a dependent variable most times we're going to use y, and derivatives of y. Okay, so a first order differential equation contains only a dependent variable, y, and its first derivative. So my dependent variable x or t, y, and y prime. Okay, so for example, y prime is equal to x, y plus x squared. Okay, and I may give you what we call a condition on y, such that y of x naught is equal to y naught. You may get something like y prime is equal to y times 1 minus y. Okay, y of x naught is equal to y naught. And you may get something like y prime is equal to x squared. Let me use a different variable. Let's use t. T times y, t squared times y squared, and then y of t naught is equal to y naught. So all of these are first order differential equations, and the goal is to solve for y of x. So the goal is to solve for y equal to f of x, or y of x, or y of t. Okay, so this is what we consider to be a differential equation. All right, and it's first order because it only has y prime. So if I have something that looks like this, which we're not going to do, but y double prime plus ty prime plus 5y is equal to 0. This is second order, and we're not going to touch that in this class. Second order because it has two, it's the second derivative. So we're only going to be looking at the first three. Okay, so it's going to be given to you dy dx or dy dt. Let's use dy dx is equal to a function of x and y. All right, so I know, so basically I'm telling you what the derivative of the function looks like at every x and y. And you have to go back and find what the function actually looks like. Okay, so this is what we have as a, excuse me, as a problem. Okay, and sometimes you may or may not be given the y of x naught is equal to y naught. If you don't have that, you're going to get a general solution. If you're given y of x naught equals y naught, you're going to have a specific solution. Okay, one solution. Okay, so what we want to talk about here are direction fields. So I'm going to just give you an idea of what direction fields look like. Okay, so the first thing is if the function only has the right-hand side as a function of y, we consider that to be autonomous. Okay, so if f of xy is only a function of y, then the differential equation is autonomous. Okay, so one of the easiest ones to start with as an example is dy dx is equal to y. Okay, so now the reason why that is the easiest one is because we already know the answer to this. What is the only function who is equal to its derivative? There's only one.
Isn't it e?
That's right, it's the exponential. Thank you, Lawrence. Okay, so the only function who's equal to its derivative is the exponential, and it could be any constant times the exponential. So we're going to, so we already know that the solution is y is equal to a constant times e to the x, because if I take dy dx, I get that constant times e to the x. So that's the only thing that works. Nothing else works. Okay. So the way you draw a direction field, what do you know? So given any, let me start again. Given any function y of x, what does dy dx represent? What does dy dx represent?
Would that just simply be like a slope or change?
That is the slope. Good. All right, so dy dx is the slope. So that is the slope of y, or the slope of the tangent line to the curve y of x. So dy dx represents the slope. So now look at what we're telling you. So when I give you dy dx is equal to y, I am telling you that the slope of the function is always equal to whatever y is. Okay, so dy dx equal to f of x, y. That says that the slope of the function or the solution, the slope of y of x is equal to the function f at xy at each point. So therefore, if I tell you dy dx is equal to y, I am essentially saying the slope of the solution y of x is always equal to the current value of y. So let's draw that. Okay. I'm gonna change my view of my here. Okay, so I'm going to change my grid. All right, now mine needs to be a lot more precise than yours in order for you to understand this. So I'm going to try to do the very best I can. All right, so I am using the fact, I'm going to write it over here, that dy dx is equal to y. And what we're getting ready to draw right now is called a direction field, also known as a slope field. Okay, this can be pretty tricky, so don't write if you can't write and look at the same time, then just look. I'll give you time to write. Okay. So here's my grid. And this is x, and this is y. Okay, so right here, at this line, the x-axis, y is equal to 0. And so if y is equal to 0, I'm going to go to every point. So let's look at the point 0, 0. So at the point 0, 0, I need to move this down. So you and move you down. Good. Okay. So I've said to you, dy dx is equal to y. That's the problem I'm trying to solve. That says that at every point, the slope is equal to whatever the y value is. So at the point 0, 0, y is 0. So at the point 0, 0, I'm going to draw a little line of slope 0. At the point 1, 0, y is still 0. So I'm going to draw a little line of slope 0. At the point 2, 0, I'm going to draw a little line of slope 0. At the point 3, 0, little line of slope 0. 4, 0, little line of slope 0. Okay, here, same thing. -1, 0, little line of slope 0. Little line of slope 0, a little line of slope, because y is 0 on this whole line. So since y is 0 on this whole line, I'm going to draw little lines of slope 0 at every value. Okay, I don't have to do too many, but I did a lot. Okay. So that was y is equal to 0. So now if I go to the next line, y is equal to 1. So up here, right here, y is 1. So that means at every point, I'm going to draw a little line that has slope 1. Now, how can I do that? So in order to draw a little line of slope 1, that means if I were to get slope 1, I would start at this point, I would go up and over, I would have a little line that looks like that. And now I'm going to draw a little red line of, back up. Come on now, you're supposed to be red. I'm going to draw a little red line of slope 1. Okay. Again, a little red line of slope 1. If it's slope 1, it goes to the next corner. A little red line of slope 1, because y is 1 on every one of these spots. So therefore, the slope is 1 on every spot. Okay, so if you notice, I'm just trying to make it match up like that. I'm just trying to make it match up. Okay, same thing on the negative values, the slope is still 1. Slope is still 1. Doesn't matter what x is, I know y is 1. So I'm good with that. Okay. All right, how about down here? Well, y is -1 down here. So that means I'm going to draw a line with slope -1. So if I were here, I'd be looking at going in that direction. So now I have a line of slope -1. If I were here, I'd be looking like that. So I have a slope of -1. So I draw a little line. It only depends on y now, only depends on y. This is an autonomous problem because the right-hand side only depends on y, and all of these lines have slope -1. Okay, any questions so far?
Is the one at the bottom negative?
Yes, it is. I just forgot the negative. I apologize. Thank you. Okay. All right, let's go up. Y is 2. All right, now this one's a little tougher because now on this whole row right here, this whole row, y is 2. So that means the slope has to be 2. So now the slope looks like start here at this point, go up 2 and over 1. So now my line looks more like that. So if I go up 2 and over 1, my line looks like that. Up 2 and over 1, my line looks like that. So my slopes now are looking like this. So my slopes are going to be in that direction. So this slope is now in that direction. This slope is now in that direction. This slope is in that direction. This slope is in that direction. So is this one. So is that one. So is that one. So is that one. On this side, same thing. Go up 2 over 1. So here's, you can see. Gives you an idea of what your slope actually looks like. So notice that my dark lines, which I'm plotting the slope. So at the point 2, 2, the slope dy dx has to be the y value. So the slope is 2. So what do you think is going to happen down here where y is equal to -2? I'm now going to make my slopes be -2. So now they have to go like, yeah, it's a good thing, make them gray. Now they have to go like this. Oh, that's in the wrong place. Sorry, guys. I don't want to go from that point. I want to go from the next point. Wrong, 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 wrong. From here, the slope from this point, the slope is like that. Okay. So all of those have slope -2. So now let me go back and make them slope -2. So it has to be in the same direction as that line, which is slope -2. I'm going to do one more because then they start to get really hard. Okay. All right, if y is equal to 3 here, then all the slopes now at these at what have to be of slope 3. Okay, so now all the slopes I want at the next points are 3. So that means if I'm at this point right here, I'm going to go up 3 and over 1. And so now my slopes look like this. See how the slope is 3 now? Up 3 over 1, up 3 over 1. So see how the slopes are getting steeper? Because why are the slopes getting steeper? Well, y is increasing. So if y is increasing, the slopes are getting steeper. Okay, this one's going. Okay, so now we can draw in the slopes that are 3, and notice they are getting pretty steep, so they're getting harder to draw. Because we don't want to draw a straight line because they're not straight, but they have slope equal to 3. And at the next line, they would have slope equal to 4. And at the next one, they would have slope equal to 5. So come down here and do the same thing. So I go, slope is -3. So I'm going to go over and down 3. So now I'm looking like this. Okay, and then we're going to draw in our slopes. And after we draw in our slopes, we're going to imagine that we filled this whole grid like this. Now, as you can see, this is what I want you to think of. I want you to think of this as water. Okay, so if you think of this as water and you're a particle, so think of you as a particle that got caught in the water. So if you're a particle, let's say I'm a particle right here. I don't want to be red, I'm going to be blue. You're a particle that got caught right here. If that's the case, then you got swept up just like this. If you're a particle back here, you got swept up just like this. Suppose I'm a particle right here. I might have got swept down just like this. Okay, I don't know if you guys can see it, but this blue line is literally the solution. Y is equal to a e to the x, where a is the value where it crosses right there. And this blue line down here is y is equal to a e to the minus x. And again, this is where it is caught right here. That's its value. Okay. So now, as you can see, this is the solution of what happens to, so we found the solution to the problem. Okay, so the solution to the problem is y. So these are what we call direction fields. All right, so only direction field, the slope only depended on the value of y, not the value of x. All right, so here's one from your book. I like this one because this one is really cool. Let me see if I can grab it. Come on now, let me grab it. Get it. Why won't you let me get it? Come on, go back. Okay, I got it. Okay, so this one comes from your text. All right, so here's the problem. The problem is solving the differential equation t prime is equal to negative 0.4 times t minus 42. And this is a differential equation that describes in Newton's law of cooling. And if you plot its direction field looks like this. Okay, so notice, let's choose a value. So if I chose, so right here, this is the line, this line right here, where it is straight. Well, what is that line? Well, let's see. If I set the slope equal to 0, t prime equal to 0, then I would get negative 0.4 times t minus 42 is equal to 0. So that would tell me t minus 42 would equal 0. So t would equal 42. So where the slope is 0 would be right at this point t, and right there t would be 42. Okay, that is called an equilibrium point. Okay, so an equilibrium point that's where dy dx is equal to 0. In other words, the slope is 0. So the rate of change is 0. So the solution is not changing. So along this line right here, the solution is always 42 because its rate of change is 0. Okay, these are places up here where dy dt prime, so above the x-axis, t prime, I'm sorry, above t equal to 42, t prime is negative. And note that the solution is decreasing down to t equals 42. Here, t prime is greater than 0. So the solution is increasing to t equal to 42. We also say the solution is stable. So a point is stable, a point x naught, y naught is stable if the solution y of x going through the point X naught, Y naught tends to an equilibrium. Okay. Let me see what else I have here on this. Okay. Here's one more. Y prime is equal to 3x plus 2y minus 4. Y prime is equal to 3x plus 2y minus 4. Okay, this one is definitely not autonomous because it depends on x. And here is its direction field. Again, at every point, you can figure out what the direction field is. So let's see. At the point 0, 0, what is the slope? dy dx at the point 0, 0 is -4. And notice that's what the slope looks like right there. The slope is -4. Okay. So if I were to take and draw this line straight up, it goes right up there. So that thing has slope -4 at that point. Can everybody see that? And if I were to go the other direction, it's still slope -4. So at every point, you just plot the slope, which is a function of x and y. All right, so this here, f of xy, whoops. F of xy is equal to 3x plus 2y minus 4. Okay. Please look in the book because the book online has some really nice pictures. Okay. All right. Okay. Let's talk about Euler's method. All right, so Euler's method says, suppose I don't know how to solve the differential equation. We're going to learn how to actually solve these differential equations tomorrow. But suppose I don't know how. Okay, I don't know what to do. Euler's equation says, well, let's approximate what the derivative is by using the definition of the derivative. Okay, so what's the definition of derivative? So given y of x, we know y prime of x is equal to the limit as h approaches 0 of y of x plus h minus y of x all over h. Okay, so that should look pretty familiar to everybody as the derivative. All right, so that's the definition of the derivative. And you guys remember back in Calc 1 when you had to use the definition of derivative to find it, and it was pretty hairy, scary. But that's the definition of the derivative. Well, if h is really, really small, we write h is much less than 1, or h is really, really small. Then we get y prime of x is approximately y of x plus h minus y at x all over h. Okay. Now let's multiply by h. So I get h times y prime at x is approximately, remember h is still small, y at x plus h minus y at x. And more importantly now, I see that y at x plus h is approximately y at x plus h times y prime at x. Now, I'm trying to solve y prime at x is equal to a function of x and y. Why don't I plug this in here? And now I get that y of x plus h is approximately y at x plus h times f of x and y. And this thing has a name. This is called Euler's method. Okay, now why does that help me? Suppose I'm trying to solve y prime is equal to f at x, y, and I'm given y at some x naught is equal to a value y naught. So here's my grid. All right. And here is, let's say, x naught. Here is x1. The difference between these two is h. Here is x2. The difference between these two is h. So I'm going to let the difference between any x1 and x2, or any two x's, be h. And I know this is the value y naught right here. So I know y of x naught is equal to y naught. Well, if x1 is x naught plus h, then I know that y of x1, which is y of x naught plus h, that's going to be approximately, let's do approximately, y at x naught plus f of x naught and y naught. So now if I put x naught and y naught into the problem on the right-hand side, so if I put x naught and y naught into here, whatever my function is, and put x naught into here, then I will get y1. So therefore now I can find y1. If I put y1 in, I can find y2. If I put y2 in, I can find y3. If I put y3 in, I can find y4, and I can then get a picture that's going to tell me what my solution of the differential equation is going to look like based on my starting point. Okay, that's called Euler's method. So let's do something easy. Dy dx is equal to y at 0 is equal to 3. Okay, so now I know that x naught is 0 and y naught is 3. Now you have to you're probably going to be given how far out to go, or they're going to tell you what h is. Okay, so let's find an estimate. For y of 1 given h is equal to 0.2. Okay, we're running out of time, so I'm going to be ending soon. So I already know I can draw this. I know x naught, so here's x. Oh, let me draw. Yeah, here's x naught. This is x. So x naught starts off at 0, then we're going to have 0.2, 0.4, 0.6, 0.8, and then 1.0. So I'm going to compute those. And so I already know that y is 3. Okay, so in order to compute y1, I'm going to need y0 plus h times f of x0, y0. y1, sorry, y2 will be y1 plus h times f of x1, y1. y3 will be y2 plus h times f of x2, y2. And so you keep going until you get to what number we want. So this one is y0. This will be y1. So this will be n equals 0. Let me draw another line. Okay, so when n is 0, n is 1, n is 2, n is 3, n is 4. So we actually are trying to get to y5, and we will do that tomorrow.